In this video, we're going to look at how to sketch a curve using calculus. For our example, we're going to be sketching the curve y is equal to x to the 4 minus 4x cubed plus 3, showing the y-intercept, stationary points and its nature, and the points of inflection. Our first step is to find the y-intercept. To find the y-intercept, what we need to do is to substitute x is equal to 0 into the original equation and solve for y. And the reason for this is because every single point on the y-axis, your x is equal to 0. So now we start off with the equation, we replace the x with 0, and when we evaluate this, we're going to get y is equal to 3. So this means that our y-intercept is 3. Next, we're going to find the stationary points and determine its nature. I'm going to break this up into two parts. The first is to find the x values of the stationary points, and then for each x value, we're going to determine whether it's a local minimum, maximum, or horizontal point of inflection. To start off, let's find the stationary points. To do this, we need to solve for dy on dx is equal to 0. So given our function y is equal to x to the 4 minus 4x cubed plus 3, taking the first derivative, dy on dx is equal to 4x cubed minus 12x squared. And we're going to equate this to 0 and solve by factorizing. So we get 4x squared outside the bracket times x minus 3 is equal to 0. And when we apply the null factor law, we're going to get our solutions as x is 0 or x is equal to 3. So this means that our stationary points occur at x is equal to 0 and x is equal to 3. Now that we have found the stationary points, our next step is to determine the nature of each of those stationary points. We can do this using the first or the second derivative method. Because our function y is equal to x to the 4 minus 4x cubed plus 3 is a polynomial function that's easy to differentiate, I'm going to choose to use the second derivative method. So from our function y, we found the first derivative. We differentiate again to get the second derivative. D squared y on dx squared is equal to 12x squared minus 24x. If you remember, the second derivative gives us the concavity of the curve. So if d squared y on dx squared is greater than 0, the curve concaves up and we're going to have a minimum turning point. If d squared y on dx squared is less than 0, the curve concaves down and we're going to get a maximum turning point. But if d squared y on dx squared is equal to 0, that tells us that we have a possible point of inflection. So for x is equal to 0, we're going to sub this value of x is equal to 0 into the second derivative and evaluate. When we do this, we get d squared y on dx squared is equal to 0, which tells us that this is a possible inflection point. But because it's also a stationary point, we can then conclude that we have got a possible horizontal point of inflection at x is equal to 0. And we will require further testing at x is equal to 0. When x is equal to 3, we're going to do the same thing. We're going to sub this value of x into d squared y on dx squared expression and evaluate. So when we do this, d squared y on dx squared is equal to 36, which is greater than 0, which tells us the curve concaves up and we're going to have a minimum turning point. So we've got a minimum stationary point at x is equal to 3. And in order to find the coordinate, we're going to sub this value of x is equal to 3 into the equation for y to work out the y coordinate. And when we do this, we're going to get y being equal to minus 24. So therefore, we have a minimum stationary point at 3, negative 24. So far, we have found the y-intercept at 3, a minimum stationary point at 3, negative 24, a possible horizontal point of inflection at x is equal to 0. Our last step now is to find the other points of inflection. In order to find the points of inflection, we start off using the fact that d squared y on dx squared is equal to 0 gives us a possible point of inflection. So we're going to solve for this, and then we need to check on both sides of x to see if concavity changes. So starting off with the second derivative d squared y on dx squared is equal to 12x squared minus 24x, we equate this to 0 and factorize in order to solve for x. So after we factorize, we apply the null factor law to get x is equal to 0 or x is equal to 2. And this means that we only have a possible point of inflection at x is equal to 0 and x is equal to 2. The last part is to verify the points of inflection. At the point of inflection, the concavity of the curve changes. So what we need to check for is that there is a change in concavity going from the left to the right-hand side of x. And we can do this using the second derivative. Remember, when the second derivative is positive, the curve concaves up. And when it's less than 0, the curve concaves down. So we're looking for different signs on the left and the right-hand side of x for the second derivative. So starting off with x is equal to 0. On the left of x is equal to 0, we're going to choose x is equal to -1. And when we sub x is equal to -1 into the second derivative expression and evaluate, we're going to get 36. And we do the same for x is equal to 1, sub this into the second derivative expression and evaluate, and we're going to get -12. So at x is equal to -1, the second derivative is positive, which means the curve concaves up. And at x is equal to 1, the second derivative is negative, which means the curve concaves down. So there is a change in concavity on the left and the right-hand side of x is equal to 0. But because we also established that x is equal to 0 is a stationary point, this means that at x is equal to 0, we have a horizontal point of inflection. So now let's look at x is equal to 2, where we're going to check on the left of 2 at x is equal to 1. When we sub x is equal to 1 into the second derivative and evaluate, we're going to get -12. And when we sub x is equal to 3 into the second derivative and evaluate, we're going to get 36. So at x is equal to 1, the second derivative is negative, which means that the curve concaves down. And at x is equal to 3, the second derivative is positive, which means that the curve concaves up. So that means we have a change in concavity. So at x is equal to 2, we have a point of inflection. And then what we do is we sub these values of x into our original y expression to get the coordinate of the points. Now that we've found all the important points on the curve, our last step is to sketch the graph. So here's a sketch of the graph y is equal to x to the 4 minus 4x cubed plus 3. We've got the y-intercept at 3. We've got a minimum stationary point at 3, -24. We've got a horizontal point of inflection at 0, 3. And we've got a point of inflection at 2, -13. Thank you everyone for watching the video. If you enjoyed this video, don't forget to give it a thumbs up and subscribe. We release videos across various math topics weekly, and we would love to see you all in the next one. Bye for now.